Welcome to the most comprehensive yet straightforward online resource about Linux NetFilter and iptables firewalls. Nowadays, Linux powers the internet servers and iptables is the built-in and de facto way used to secure them. This is the only course you need in order to master all iptables key concepts from scratch. At the end of the course, you'll know how to create custom iptables firewalls for your Linux infrastructure and how to troubleshoot and monitor existing ones. Now let's be honest, there are hundreds of free tutorials out there. Why should you choose this course? Because I will not only teach you some iptables commands or how to copy and paste confusing out-of-the-box configurations, but I will teach you how to deeply understand the way a firewall works and how to optimize such a security solution. I've spent thousands of hours studying Linux and security, and I honestly say that I've read them all, and it will be my pleasure to share this knowledge with you in a structured and easy to digest manner. We'll dive deeper into every iptables option, match or target, and we'll see a lot of examples, many of them ready to be used in your environment. You'll see how to filter huge collections of addresses and networks or even entire countries using IPsec. By enrolling in this course, you get the skills to get ahead. This course is really different, and I'll give you only two main reasons why you should take this course. For each iptables key concept, you'll get not only a video tutorial, but a bunch of real-world examples, quizzes, challenges with solutions, and slides with main points. This course is taught by me. Hi there, I'm Andrei. I have almost 20 years experience in networking and programming, and I'm not just a random guy that teaches Linux and iptables. I have more than 10 years experience with in-person networking and programming trainings. Over the years, thousands of students have been enrolled in my courses. I know how to build a curricula, and I know exactly what really matters. This course is for a wide audience, including sysadmins, network engineers, DevOps engineers, ethical hackers, pen testers, and anyone who is involved with Linux and security. And don't forget, you'll have lifetime access to the course, and you can return and look for a specific iptables option, match or example anytime you want. And one more thing, I'll update the course constantly with new content, quizzes, and challenges. Now, if you don't like the course, you are covered by a 30-day money-back guarantee, full refund, no questions asked. When you are ready to start your journey into Linux and NetFilter iptables firewalls, check the free preview lectures to see if the course is right for you, and then click the enroll button. See you in the course. Hello and welcome. In this course, we'll talk about Linux firewalls. A firewall is a network security system that monitors and controls incoming and outgoing network traffic based on predetermined security rules. A firewall typically establishes a barrier between a trusted internal network and untrusted external network, such as the internet. Firewalls are an important tool that can be configured to protect your servers and infrastructure. The firewall solution for Linux is called NetFilter. NetFilter is a software firewall, a packet filtering framework inside the Linux kernel. It enables packet filtering, network and port address translation, port forwarding, and packet alteration, which is the process of intentionally altering data in IP packet headers before or after the routing process. NetFilter is the professional and mostly used solution for building firewalls in Linux operating systems. The netfilter framework is controlled by the iptables command. iptables is a tool that belongs to the user space used to configure netfilter. It is said that netfilter belongs to the kernel space and iptables belongs to the user space. Most of the time, netfilter and iptables are often combined into a single expression, netfilter iptables. In this course, we won't make a very clear distinction between iptables and netfilter and simply refer to the entire thing as iptables. Then you should know that every Linux distribution uses netfilter and iptables, and there is nothing extra, no extra software that should be installed. iptables is already there. You should also know that only root can configure the netfilter framework or use the iptables command. This was a very short introduction to netfilter and iptables, and in the next lectures we'll dive deep into almost every iptables option available. In this lecture, we'll take a look at iptables, chains, and tables, which are extremely important netfilter concepts. In order to be proficient in building custom firewalls, you have to deeply understand these concepts. Every data packet is inspected by firewall rules within the Linux kernel. Firewall rules determine what traffic your firewall allows and what is blocked. Each rule has a matching component and an action component. When packets arrive from the network, the netfilter framework of the Linux kernel recognizes and groups packets into data streams or flows. Netfilter analyzes both packet headers and packet contents in order to track connections and to perform SPI or stateful packet inspection. Each packet from the stream is processed by the firewall with some performance optimization. The iptables firewall uses tables to organize its rules. Within each iptables table, rules are further organized within separate chains. Rules are placed within a specific chain of a specific table. This is important, and I'll say it again. A rule is connected to a chain and to a table. Within a chain, a packet starts at the top of the chain and is matched or evaluated rule by rule. When a match is found, the target of the rule is executed. The target is the action that is triggered when a packet meets the matching criteria of a rule. Examples of targets are drop or accept. If the target is a terminating one, like for example drop, no other rule will evaluate the packet. If the packet reaches the end of the chain without a match, the default policy for that chain is applied. There are two policies, drop and accept, and the last one being also the default one. We'll talk more about policies in subsequent chapters. Let's move on and see what chains are available in netfilter. There are 5 built-in chains. One of the most used chains for packet filtering is called input. This is used for filtering, so dropping or accepting incoming packets. Our Linux host is the destination of the packet. Each packet that was destined to our Linux host is evaluated against the rules of input chain. No exception here, no packet is allowed to skip this evaluation. I'd like to show you a very simple example. Please don't focus on iptables syntax, but only on the concepts of chains, tables, rules, and targets. From this Windows machine, I'm gonna continuously ping the Linux machine. Ping -t and the IP address of the Linux machine. And on the Linux machine, I'm gonna add a new iptables rule to filter table of input chain that drops all ICMP traffic and that includes ping as well. I'm becoming root. And I'm writing the rule iptables -t filter -a input -p ICMP -j drop. Ping is still working. And we notice how ping has suddenly stopped because the NetFilter firewall is blocking incoming ICMP, so including ping packets. Ping doesn't work anymore. By the way, you should always write table names in lowercase letters and chain names in uppercase letters. Targets like drop in our example are always written in uppercase letters. Another important chain is output. This is used to filter outgoing packets. Our Linux host is the source of the packet. Let's see an example. I want to drop all packets generated by the Linux host that are going to the IP address of netfilter.org. First, let's check that the connection is working. And we see that the site is loading. Now, I'm adding a firewall rule to filter table and output chain. iptables -t filter, this is the name of the table, -a output, the name of the chain, -d netfilter.org, and -j drop. This is the target or the action. Let's check again the connection to the website. I'm refreshing the website. We notice the web page is not loading anymore. Of course, that's because the firewall is dropping generated packets that are going to netfilter.org. One remark here. Netfilter uses in fact the IP address of netfilter.org, not the domain name, even though I've written the domain. Behind the scenes, it makes a DNS query and requests the IP of netfilter.org and then drops all the packets destined to that IP. Now, in your tasks, if you are using another domain, especially a big one like google.com or facebook.com, it's possible that even though you've executed the right iptables command, the connection to that site is still working. The reason for this is that behind those big domains, there are tens of IP addresses and you've blocked only one or a few of them. When you make the next DNS request, it's possible that the server will give you a new IP that was not blocked in the first place. As a conclusion, you can deny access to the websites this way only if that domain has one or only a few IP attached. Another chain is forward and is used for filtering routed packets. In this case, our Linux machine is a router and connects at least two networks like the internet and the local area network. And the last two chains are pre-routing, used for DNet, aka port forwarding, and post-routing, used for SNet or simply net or masquerade. These are more advanced concepts and we'll see examples in their dedicated sections. Okay, these are the 5 iptables built-in chains. They are always available, you cannot remove or rename them. You just use them as they are. You can also create other chains named user-defined or custom chains. This is an advanced topic and we'll dive deeper into user-defined chains and we'll see many more examples in another section. Welcome back. Let's take a look at the tables that iptables provides. The logic for filtering IP packets is organized in a collection of tables, each with a specific purpose. Each packet is inspected by the NetFilter firewall and matched in order top to bottom against the rules that are placed within a specific chain of a specific table. There are 4 built-in tables available, and each table has a very specific purpose. The filter table is one of the most widely used tables in iptables. It's the default table and is where all the actions typically associated with a firewall take place. There is where the decision of accepting or dropping each packet is taken. Being the default table means that when we add or remove a firewall rule, if we don't specify the table's name, it will automatically consider the filter table. Let's see an example. I want to create an iptables rule that accepts TCP traffic to port 22 only if it comes from a specific IP address. This is the Windows machine and this is the Linux machine. Let's check port 22 on Linux from Windows. Let's see if it's open or closed. Telnet, the IP address of Linux, and port 22. Sorry, port 22. And it's open. There is an SSH server that is running. Now I'll write the iptables rules. iptables -a input -p TCP, it's TCP traffic, -d port 22, traffic is going to port 22, so the SSH server, -s, and I'll take a random IP address, -j, accept. If a TCP packet comes from this random IP address to port 22, it's accepted. Okay, let's think for a moment what happens if the packet comes from a different source IP address. And the answer is that it depends on how the policy of the input chain is set. It could be either accept or drop. The default policy always applies at the end of a chain only, and it determines what happens to the packets that are not matched against any rule of the chain. Are they accepted or dropped? In this case, we don't know what is the policy, and we neither want to enter into further details about chain policy, so we add a second rule that drops any packet to port 22 from any source address. So iptables -a input -p TCP -d port 22 -j drop. What do these two rules do? Each incoming packet will be inspected in order, and this is the key here, by the first rule, and if it doesn't match against it, it will be inspected by the second one. So if a packet is coming from 5.3.6.6, it will be accepted, and the second rule will not evaluate the packet anymore. But if it's coming from another IP address, like say the IP address of Windows, the second rule will inspect it, and if it comes to port 22, it will be dropped no matter of its source IP address. In these rules, you notice I didn't specify the table to which the rules are added. In this case, it's the filter table. Let's check the same port again. And we notice that the port is now filtered. That's because the Windows machine doesn't have that specific IP address, and only traffic from that IP is permitted. Also note that iptables filter table has the following built-in chains: input, output, and forward. Another table is net, and it's specialized in SNet that comes from source network address translation and DNet that comes from destination address translation. As packets enter the network stack, rules in this table will determine whether and how to modify the packet's source or destination addresses in order to impact the way the packet is further processed. iptables net table has the following built-in chains: pre-routing for DNet or port forwarding, post-routing for SNet or masquerade, and output if we want to configure net in a different way for locally generated packets. The mangle table is specialized in packet alteration. For instance, we can modify fields in the IP header, like say type of service or time to leave, by adding rules to the mangle table. The mangle table has the following built-in chains: pre-routing, input, forward, output, and post-routing. In fact, it can be used with all iptables built-in chains. And the last table is RA. The iptables firewall is stateful, meaning that packets are evaluated in regards to their relation to previous packets. iptables views packets as part of an ongoing connection or session instead of as a stream of discrete, unrelated packets. The RA table is used to set a mark on packets that should not be handled by the connection tracking system, or simply said, we don't want some packets to be classified by accepting them directly. Like for example the traffic from our own loopback interface. This is done for performance improvement. We'll have a special section on RA table later in the course. To write efficient firewall rules, you must deeply understand how a packet traverses the net filter tables and chains. And there are 3 lectures where I explain in depth these concepts. Until that point in the course, to ensure a smooth start in understanding iptables, let's recap in a nutshell the most used scenarios. Incoming traffic is filtered on the input chain of the filter table. Outgoing traffic is filtered on the output chain of the filter table, and routed traffic is filtered on the forward chain of the filter table in both directions. Then, source network address translation, SNet or masquerade, is performed on the net table of the post-routing chain, and port forwarding or destination network address translation is performed on the net filter of the pre-routing chain. Now, if we want to modify values from the packet's headers, like time to leave or type of service, we add rules to the mangle table of the output, pre-routing or post-routing chains. And if we want the packet to skip the connection tracking system, we add rules that match that packet to the RA table. Okay, that's how a packet traverses the net filter tables and chains in a nutshell. Thank you. In this lecture, we'll talk about the iptables command. iptables is the user space component used to configure netfilter, the kernel framework that does the actual filtering. It's said that iptables belongs to user space and netfilter belongs to kernel space. So we can interact with netfilter using the iptables command. There are also some graphical frontends for netfilter that allow us to create rules. However, they lack the flexibility of using a command line, and Linux professionals rely heavily on the iptables command, which has many options. It is also important to know that iptables can be run only by root. Let's move on and see what is the general syntax of iptables. After the iptables command comes the table name. The table name indicates the netfilter table on which the command operates. By default, it's the filter table. Command or option indicates the operation we perform on a chain of that table. Either long or short options are allowed. For example, we append a rule to the end of the chain, we insert a rule on a specific position, we flush all the rules of a specific chain and table, or we simply print out all the rules of a chain. Each rule has a matching and an action component. The matching part of a rule specifies the criteria that a packet must meet in order for the associated action or target to be executed. A match is something that specifies a special condition within the packet that must be true or false, and a single rule can contain several matches, and the entire rule condition is true if all the matches are true. For example, we may want to match packets that come from a specific host or network and are going to some ports on our system. If any of these matches fails, for example, the source address isn't correct, but everything else is true, the whole rule fails and the next rule is tested on the packet. But if all matches are true, the target specified by the rule is applied. Then comes -j and the target. The target specifies what action is taken on packets matching the criteria of the rule. Examples of targets are drop, accept, log, or masquerade. We'll dive deeper into targets in a dedicated section. Enough talking, let's go to a terminal and write some real iptables rules. Before starting writing rules, don't forget that only root can run the iptables command. You need root access in order to configure netfilter or run the iptables command. If you try to run the iptables command as a non-root user, you'll get a permission denied error. I've executed the iptables command as a non-root user, and I've got a permission denied error. It says very clear that I must be root. And I'm becoming root by running sudo su. Now I'm root. Let's run the same command as root. Okay, there is no error. By the way, the command lists the filter table, which is the default for input, output, and forward chains. If you want to see the rules from other tables, you should specify the table using -t option like this, iptables -tnet -l. It has displayed the chains of the net table. Okay. In the next example, I want to add a rule to filter table and input chain that drops incoming ping packets. First, I'm checking that ping is working. Ping and the IP address of Linux 1. This is another Linux host and its host name is Linux 2. So ping and the IP address of the other Linux operating system. X10 at the end. Ping is working. And now the rule. iptables. I'm adding the rule to the filter table, filter. -a, I am appending the rule to the input chain. And the matches. The protocol is ICMP, --ICMP type. I'm matching on the ICMP type. Echo. There are more messages in the ICMP protocol and I am dropping only echo or echo request packets. minus J, drop. Ping is still working, and I'm hitting enter. Okay, it wants echo request, not echo. Perfect. And we notice how ping stopped. Let's list the contents of the firewall. iptables minus L or iptables minus VNL. I want to see more information. And there are 30 packets matched by the rule. The same rule could be applied without -T filter option. The filter table is the default. It's the same. Let's try another rule. I want to deny access from this Linux host to a specific website, let's say www.ubuntu.com. Let's think about this requirement and split the rule in more parts. What table are we using? And the answer is filter, because we are filtering traffic. We are not doing net or something else. So iptables minus T filter. What iptables command or option are we gonna specify? And the answer is -A from append. We are gonna append a new rule to the table. What chain will be used to match the packets? This is outgoing traffic and it always means output. And now come the matches. What matches are required for this kind of traffic? So this is TCP traffic minus P from protocol TCP minus D port 80. The traffic is going to port 80. And minus D, the destination IP address, www.ubuntu.com. And what target or action we perform on the matched packets. And of course, it's drop. -J, drop. J means to jump to the specific target or do the following action when the packet matches against this rule. Targets are always written in uppercase letters. Before hitting enter, I want to check that the web page is loading. And the page is loading. We notice here that it uses HTTPS and that means port 443. So I'm hitting enter and I'm adding another rule that drops packets to port 443. So in fact these two rules will block traffic to port 80 or port 443. Let's reload the page. And we notice that the page is not loading anymore. If we list the firewall using -L option and VN, okay, we see the iptables rules and a lot of matched packets on the output chain. All these IP addresses are of www.ubuntu.com and have been obtained from the DNS server. And we see a lot of matched or dropped packets. Hello and welcome back. In this lesson, we'll talk about iptables options, flags or switches. These options specify the desired action to perform and only one of them can be specified on the command line unless otherwise stated. Also note that all of these options are written in uppercase letters. Let's see what options are available. -A means append the rule to the end of the selected chain. Let's look at an example. I'll append a rule to the output chain that drops incoming traffic to port 25. So SMTP traffic. iptables. It's not necessary to specify the table. It's by default the filter table. So I don't write -t filter. I could write if I want. -a, the name of the chain input, minus PTCP, it's TCP traffic, minus D port 25. The packets are going to port 25, minus J drop. Before hitting the enter key, I want to test that port 25 is open. From another Linux machine, I'll scan that port. And I'm gonna use nmap. Nmap minus P the port 25 and the IP address of the Linux machine that I'm scanning. By the way, you could simply install nmap by writing apt-get install nmap. And we notice that port 25 is open. And I'm adding the iptables rule. I'm scanning the port again. And the port is filtered. This iptables rule has dropped the packets to port 25. Let's add another rule that blocks incoming traffic to port 80. iptables minus A input minus P TCP minus D port 80 minus J drop. And I'm also installing a web server to test it right. It's very easy to install a web server on Ubuntu. I'm installing the Apache web server. From the other Linux operating system, I'm gonna scan port 80. The port is filtered, and if I list the firewall, I'll see a lot of matched and dropped packets. Each rule has dropped 2 packets. Another important option is -i. -i inserts one or more rules in the selected chain on a specific position or on top or position 1 if no position is given. Let's look at an example. I want to drop incoming traffic to port UDP 69, which is TFTP, Trivial File Transfer Protocol. Instead of -a, I'll use -i. The chain is input -p, the protocol is UDP, and the destination port is 69. -j drop. Now I'm listing the firewall. We see that the last rule has been added on top of the input chain. Now that rule is the first rule in the chain, and this is very important because rules are traversed in order. If I want to add a rule on a specific position, for example a rule on the second position, I can simply specify the position after the name of the chain. Like this. I'll insert this rule on position 3, on the third position. And the rule is on the third position. Let's suppose I've changed my mind and I want to accept all traffic to port 80. Remember that I've already added a rule that drops traffic to port 80. I'm running the same iptables command, just that instead -a, I'll use -i. Okay, this is the rule. I'm using -i. And instead of drop, I'm using accept. Instead of appending the rule to the end of the chain, the rule will be added on top of the chain on first position. We see the rule on first position on input chain. Pause the video for 30 seconds and think about what will happen. Will the traffic to port 80 be dropped or accepted? Let's test it using the browser from another machine. I'm writing the IP address of Linux 1. And we see that the port is open. We could connect to port 80 and the page loaded successfully. When I've added the rule using -i, the rule became the first rule in the chain, and rules are traversed in order, top to bottom. When a packet is arriving to port 80, the first rule matches the packet and accepts it. Accept is a terminating target, and that means that the packet is accepted and no other rule will check the packet. So in fact here, the rule that drops incoming packets to port 80 will never be evaluated. That's why the packets were accepted, and this is an example of why the order of the rules is so important. Another option is -l. -l lists all rules in the selected chain and the specified table. If no chain is given, all chains are listed. For example, iptables -l lists all rules in the filter table and all its chains, input, output, and forward. It's common to use -l option together with n from numeric and v from verbose like this. We'll talk more about -l in another lecture where we'll dive deeper into listing the Linux firewall. -f means flush the selected chain or all the chains in the table if none is given. This is equivalent to deleting all the rules one by one. For example, if I want to flush the input chain, I can simply execute iptables -f input. Now, when I'm listing the chains, I can see that there is no rules on the input chain. They have been flushed. If I don't specify the chain, it will flush all chains from that table, and by default, it's the filter table. It has flushed all the chains of filter table. Now, I'm flushing all the chains of the net table. We'll discuss more about -f in a subsequent chapter. -z means zero the packet and byte counters in all the chains or only in the given chain. Let me show you an example. I'll add a rule to the output chain that accepts SSH outgoing traffic or traffic to a remote SSH server, this Linux being the SSH client. iptables -a output -p TCP -d port 22. The packets are going to port 22 -j accept. And I'm connecting to a remote SSH server just to have some matched packets. Okay, I am pressing Ctrl+C. I don't want to connect to that server. I just wanted some matched packets. When I list the firewall, we see that there are 9 matched packets, or 1925 bytes. iptables -z will reset packet and byte counters. We see that the number of packets and bytes matched by the rule have been reset. -n creates a new user-defined chain by the given name. We can create user-defined chains simply by writing iptables -n and the name of the new user-defined or custom chain. iptables -n, my chain. When running iptables -vnl, we see all the chains, including the custom chain I've just created. Now to delete that chain, I use -x option, iptables -x, my chain. I don't go deeper into user-defined chains at this moment. We'll have an entire section on this later in the course. And finally, -p sets the default policy for the built-in chains input, output, and forward. The default policy specifies what happens to packets that are not matched by any rule and can be either accept or drop. The default policy is set to accept. We can change the default policy using iptables -p, the name of the chain, and then input or drop. For example, I'm setting the drop policy for the forward chain. iptables -p, the name of the chain forward, and the policy drop. This means that each packet that is not accepted by a rule will be dropped. We'll have a dedicated lecture on policies. And the last option we take a look at in this lecture is -d. It deletes one or more rules from the selected chain. We don't use this option too much because we often write all the rules in a script and then run the script. If we want to delete or modify a rule, we simply modify the script and run it again. But if you want to use the -d option to delete an iptables rule, you just have to specify the line number you want to delete like this. There are rules loaded into memory, and I'll list the filter table to see the rules. Let's delete this rule, which is the second rule of the output chain. So I write iptables -d output and 2, where 2 means the second line. And now when I list the filter table of input, output, and forward chains, we notice that the rule has been deleted. Okay, these are the most important iptables commands, options, or flags. Thank you. Until this point in the course, we've written all the iptables rules directly at console and they were loaded into RAM. If we have a firewall with many rules, it's much easier to write all these rules in a script, make that script executable, and then run it. But if we just want a simple rule that drops the traffic from a specific IP address or allows a specific service to communicate with the outside world, we can simply write that rule at the Linux terminal. Let's see some live examples. If I want to write an iptables rule at the Linux terminal, I simply write the rule as root. iptables -a input -p icmp -j drop. That's all. The rule drops all incoming ICMP traffic to this Linux machine. It's important to note that iptables rules written at the terminal are not saved after the system is restarted. If you reboot the system, you will lose all the rules. And you say, okay, but do I have to write all the rules each time the computer starts? Of course you don't. If you want your iptables rules to persist after the system restarts, you write them in a shell script, make that script executable and configure the script to be run automatically at boot time. Let's go to work and see how we create a script with iptables rules and then run the script. Remember that a script is just a text file that contains shell commands. I'm gonna create the script using my preferred text editor, which is VI. In your case, if you haven't used VI before, try a simple editor like Nano, Pico, or even Notepad. VI is a very good and efficient editor, but it's not the easiest one to use in Linux. The name of the script will be firewall1.sh. The first line of the script will look like this: a hash sign, an exclamation mark, and the path to bash. This is called shebang, and it tells the shell what program to interpret the script with when executing it. In this example, the script is to be interpreted and run by the bash shell. If you write another script, let's say a Python script, you write here the path to the Python interpreter. The most common option is using bash. And inside the file, I'll simply write some iptables rules. For example, I'll write a rule that drops all incoming SSH traffic, so traffic to port 22, and two another rules that drop outgoing traffic to port 80 and 443, so HTTP and HTTPS traffic. And the first rule, iptables -a input -ptcp -d port 22 -j drop. It drops incoming traffic to port 22. And two rules that drop outgoing HTTP and HTTPS traffic. iptables -a output x outgoing traffic -ptcp -d port 80 -j drop, and another rule for HTTPS. iptables -a output -ptcp -d port 443 -j drop. Okay, here x output. I'm saving the script, make it executable, and then run it. And we see the rules. The rule that drops incoming SSH traffic and the rules that drop outgoing HTTP and HTTPS traffic. One important thing to know is that if I run the script using its name like firewall1.sh, so without a dot, which is the current working directory, and the /, I get an error, command not found. This happens because the current working directory doesn't belong to the Linux path, so the shell doesn't look for the script inside the current directory. It's looking for commands only in these directories. Here is where the shell is looking for commands. So you have either to add the current working directory to path or run the script using ./ and the name of the script. In fact, it says take the script from the current working directory, which is dot, and run it. Now suppose we want to change something in our script. For example, I don't want to block outgoing HTTPS traffic anymore. The logical thing to do is to open the script, replace that line, save the script, and run it again. In this example, I've executed the script again. If we list the firewall iptables -vnl, we see that there are more rules that we have expected. There are only 3 rules in the script, but more rules in the RAM memory. In fact, each rule seems doubled. To make this point clearer, I'll execute the script again. Now, there are even more rules in the RAM memory. Something is wrong. What could it be? Each time I've executed the script, the rules from the script, so those 3 rules, have been appended to the iptables chains. I ran the script 3 times, so I have 9 rules. And this is not what we want as a result. When I run the firewall script, I expect that only those rules from the script are loaded. How do we do it? A good practice is to add at the beginning of the script iptables -f. This will flush all the chains of the filter table and start with a new fresh firewall. I am opening the file, and at the beginning I am adding iptables -f. This will flush all the chains. I'm saving the file and running it again. And we notice that only the rules from the script have been loaded. All other rules have been flushed. An important remark is that if you have rules also on other chains and tables, like say rules for doing net, you should also flush those tables and chains. Let's see what it's all about. I'm adding a rule that will perform as net. It will translate the private IP addresses from network 10.0.0.0/8 to the public IP of this Linux machine. In this case, it's a router. iptables -tnet, it's mandatory to specify the table, -a post routing, -s, the IP addresses that will be translated, it's an entire network, -o, the outgoing interface, -j, snet, and to source, and I'll write a random IP address. I suppose this is the public IP. Don't focus on net, we'll have an entire section on this. I'm saving the script and then run it. And I'll run it many times. When I am listing the net filter, we see there are many rules. There are 4 rules, not 1 like in my script. It appended the rule to post routing chain and not filter each time I've executed the script. This issue will be solved by also flushing the net table at the beginning of the firewall script. Here, at the beginning, I write iptables -tnet -f. I'm saving the script and running it again. I can run it as many times as I want. There will be a single net rule, the rule from the script, iptables -tnet -vnl. And there is only one rule. Okay, that's all, thank you. In this lecture, I want to emphasize the difference between iptables options -a append and -i insert. Should we use -a or -i in our iptables rules? Most of the time, we write the iptables rules in a shell script and run that script. Let's take an example. We create a script that drops incoming SSH traffic from any IP address except one. By the way, this is a very common scenario. I'm creating a new script called drop _ssh.sh. The first line will be the shebang. It tells that the script is executed by bash by default. At the beginning of the script, I'll flash the firewall. We've discussed about this in the last lecture. And the rules. iptables -t filter. Filter is not mandatory, it's the default table. -a input. It's incoming traffic, so I am using the input chain. -ptcp, --d port 22. The traffic is coming to port 22. And the source IP address I am permitting. And it's the IP address of the other Linux machine I have. And -j accept. This rule will accept SSH traffic from this source IP address. And another rule that drops all other SSH traffic. iptables. I don't write -t filter anymore. -a input. -ptcp. --d port 22. And -j drop. I'm saving the file and then make it executable. And I'm executing the script. Perfect. Let's test it. First, I'm trying to connect to this Linux machine from the IP address that was permitted. SSH, the user that is authenticating, student, and the IP address of the server. And it's working. Perfect. Now, let's try to connect to the SSH server from another IP. For example, from Windows using PuTTY. And it's not working. Let's list the firewall. We see there are 3 dropped packets by this rule and 40 packets accepted by the first rule. Perfect, it's working fine. Now back to our firewall script, we'll try something different. What would happen if instead of -a, which means append or add rules to the end of the chain, I'd use -i, which means insert or add rules on top of the chain. I'm replacing -a with -i everywhere. I'm saving the script and then run it. Let's try to connect again using SSH from the IP address that was permitted. So from Linux 2. I'm executing the same command. And surprise, it's not working anymore, but it should be working. Let's analyze what had happened. The bash shell has executed the script line by line. On this line, it has flashed the filter table of input, output, and forward chains, and on this line, it has added this rule to input chain. This is the first rule of the chain. And then it inserted this rule, so the last rule of the script, on top of the input chain. Insert means insert the rule on top. So in fact, this is the first rule of the chain and this is the second rule. Let's list the firewall to check it. We notice that the rule that drops the packets is the first and the rule that accepts the packets is the second. That's because I've used -i instead of -a. In the RAM memory, the rules are not in the order in which they were written in the script. What happened when a packet from the permitted host has arrived to the firewall? Which rule has matched the packet? And of course, it's the first rule, the rule that is dropping all traffic to port 22. The packet's headers satisfy the matching criteria of the rule. It's TCP traffic to port 22, so it's dropped. So in fact, the second rule, the one that accepts traffic to port 22 from that specific IP address, will never, but never match any packet. All the traffic has been already dropped by the first rule just before it. This is an example showing that order matters. Let's come to a conclusion. When writing rules inside a shell script, you usually use -a, so append to the end of the chain, and not -i, which means insert the rule on top of the chain. If you use -a, the order of the rules in RAM memory will be exactly the order in which the rules have been written in the script. So inside the script, we usually use -a, not -i. But when do we use -i? We use the -i option when we already have a firewall with a lot of rules and we want to drop or accept a specific IP or port by writing the iptables rule at console, so without changing the firewall script. Bear in mind that there is always the possibility to already have a rule which accepts the traffic. For example, let's say there is a rule that accepts web traffic from any IP address and I want to drop a specific IP address. Then I must add the rule that drops the traffic before the rule that accepts the traffic, and I do that using -i option. For example, at this moment, all SSH traffic is dropped, and I want to add a rule that accepts traffic from this IP address, from the IP address of Linux 2. I'm adding the rule using -i. iptables -i input -s the IP address -j drop. Sorry, I want to accept traffic, not drop it. This rule will be the first in the chain and will accept traffic from 192.168.0.20, even though there are other rules that could drop the traffic. Those rules are anyway after the rule I've just written. And you see that SSH is working. In this lecture, we'll take a look at how to obtain information about the iptables firewall. Listing the firewall means showing the tables and chains contents, and that means listing rules, the default policy, and traffic statistics. There are two main options, -s and -l. Let's take a look at some examples. iptables -l. -l is often used with -n to avoid long reverse DNS lookups. Using -n option, IP addresses and port numbers will be printed out in numeric format. We see 22 and not SSH. Then -v, which comes from verbose, shows interface names, packet and byte counters. It shows how many packets and bytes have been matched by each rule. By the way, it's very common to write iptables minus v and l. V and N are written in lowercase letters and L in an uppercase letter. In all these examples, I've listed only the filter table, which is the default. If we want to list other tables, we should specify the table's name using -t option like this: iptables minus tnet minus v and L. And it printed out all the chains of net table. Or iptables minus t mangle minus v and L. It printed out the mangle table and the raw table. There are only two chains, pre-routing and output. Okay, that's how we list the firewall. Thank you. Welcome back. This lecture will be about policy. Traffic filtering is done in the filter table of the input chain for incoming traffic, of the output chain for outgoing traffic, and of the forward chain for routed traffic. Rules are added to chains and tables and traversed in order from top to bottom by the packets. Each packet is then checked against each rule in turn, starting at the top. If it matches the rule, then an action is taken, such as accepting or dropping the packet. Once a rule has been matched and an action taken, the packet is processed according to the target of that rule and isn't processed by further rules in the chain. Now, if a packet passes down through all the rules in the chain and reaches the bottom without being matched against any rule, then the default policy for that chain is applied. The default action is referred to as the default policy and may be set to either accept or drop. The concept of default policies raises two possibilities that we must consider before deciding how we are going to organize the firewall. So when organizing our firewall, we should have the following options in mind. We can set the default policy to drop all packets and then add rules to specifically allow packets that may be from trusted IP addresses or for certain ports on which we have services running like FTP, web, email, and so on. Or the second possibility, we can set the default policy to accept all packets and then add rules to specifically block or drop packets that may be from specific IP addresses or ranges or for certain ports on which we have private services. Generally, the first option is used at least for the input chain and is considered more secure. By default, policy is set to accept any packet that hasn't been dropped by any rule. Policy can be changed for chains that have the filter table and they are input, output, and forward. We cannot change the policy for pre-routing or post-routing chains. Let's take a look at some examples. We can check the policy by listing the firewall iptables minus VNL. This is the default firewall for a Linux operating system. We see the default policy is accept for input, output, and forward chains. Note that there is no rule in the chains, so all traffic is permitted. Now, I'll continuously ping this Linux and also check the SSH connection. Ping and the IP address of Linux 1. Ping is working. And now SSH. SSH is working too. Both incoming ping and SSH are working. Now if I set the policy to drop on input chain, all the traffic will be dropped. There is no rule that accepts traffic, so all traffic is dropped. iptables minus P, an uppercase P, input drop. This is how we set the policy. We see that the policy is dropped, and it has already dropped for packets. Ping has stopped. It doesn't work anymore. Setting the drop policy on input chain without any rule that accepts traffic is like I've logically disconnected the host from the network. Now I'll add a rule that allows incoming SSH traffic. The input chain is incoming traffic, the protocol is TCP, the destination port 22 minus J, the target, is accept. Let's try to connect using SSH again. And it's working. We notice how SSH client can connect to the server again. The SSH traffic is permitted by this rule. But what about ping? Ping is still not working. Ping packets are dropped by the policy. There are 15 packets dropped. Now there are 19 packets, 22 packets, and so on. Ping is continuously sending packets to Linux One. If I want to permit incoming ICMP ping packets, I should add a rule that accepts that traffic. Also note that policy is always at the end of the chain. It's not possible to add rules that match against packets after the policy. At the end of this lecture, I'd like to tell you something important. Take care when changing the policy on remote servers. There is always the possibility to block yourself from accessing the server anymore. First, be sure that you've added a rule that allows your own traffic, and only then change the default policy. Keep this in mind. If you want to completely flush all iptables rules and reset to an open firewall state, you should set the accept policy on all chains, flush all netfilter tables, and delete all iptables user-defined chains if there is any. This is useful to use at the beginning of any firewall script in order to flush everything and build it from the ground up. I'm creating a script named delete firewall.sh. The first step is to set the accept policy on all the chains of the filter table. They are input, output, and forward. Forward chain is used only for routed packets, and that means that the Linux machine has also the function of a router. iptables minus p input accept, iptables minus p output accept, and iptables minus p forward accept. The second step is to flush all tables that have rules. iptables minus t filter minus f, iptables minus t net minus f, iptables minus t mangle minus f, and iptables minus t ra, the last table, minus f. If the table has no rule, nothing happens. And lastly, delete user-defined chains, if any. This is optionally and needed only if there are user-defined chains. We'll talk about user-defined chains in another lecture. iptables minus x. If you are using ipset to drop large collections of IP addresses like entire countries, you should also flush and destroy the sex. There will be a dedicated section about ipset later in the course. Okay, that's all. I am saving the script. Then I make it executable and run it. The iptables firewall has been cleared out and all traffic is permitted. By the way, this is also the default state of a Linux operating system. In this lecture, we'll talk about saving iptables rules from memory to a file on disk and load them back into the RAM memory at system boot time. Firewall rules created using the iptables command are stored only in the RAM memory. If the system is restarted before saving the iptables rule set, all rules will be lost. If you want your firewall rules to persist after a system restart, make sure to save them first. There are two commands that are used to dump iptables rules from the RAM memory to a file and respectively to load rules from a file into memory. These two commands are iptables save and iptables restore. The first command dumps rules to standard output or to a file, and the second one loads rules from a file into memory. Let's see how they work. I'm executing a script that contains some iptables rules. At this moment, there are some iptables rules loaded into memory. I'm listing the firewall. And there are some rules loaded into memory. And I'm running iptables minus save. Iptables minus save is dumping the iptables rules to standard output, which is the terminal. Using output redirection, I can redirect and save them to a file like this. iptables minus save, the output redirection, which is the greater than sign, and a file. Let's say my firewall. The output has been redirected to my firewall, and the file has been created. I am listing the file. And we see the output of the command. At a later moment, I can load the saved rules into memory by running iptables minus restore and the name of the file, like this. iptables minus restore and the file. My firewall. The rules have been loaded from file into memory. Good. Let's see how to restore the iptables rules after system restart. The solution is based on the Linux distribution we are using. Let's see how it's done on Ubuntu and Debian-based distributions. There is a package, a program named iptables persistent. This program is not installed by default in Ubuntu, but it belongs to the standard repositories and I can easily install it. I'm gonna install iptables persistent. I'm already root, so it's not necessary to prefix commands with sudo, and I'll simply run apt update && apt install iptables minus persistent. During the installation, you will be asked if you would like to save the current iptables rules, the rules from the RAM memory, and set them to be automatically loaded at system boot time. Select yes if you are happy with your current configuration and you have tested your ability to create independent SSH connections to this Linux machine. In my case, I'll select no. And the same for IPv6 rules. Once the installation is complete, you'll have a new service called iptables persistent that is configured to run at boot time. This service will load your iptables rules into memory and apply them when the Linux machine will start. iptables persistent will automatically load the rules from /etc/iptables/rules.v4 for IPv4 or rules.v6 for IPv6. The next step is to save the iptables rules using iptables save command to /etc/iptables/rules.v4. Let's do it. There are some rules in the memory, and I'm running iptables -save. As we've already seen, iptables save is dumping the iptables rules to standard output, which is the terminal. And using the output redirection, I'll save them to /etc/iptables rules.v4. This file will be loaded automatically into memory by iptables persistent at boot time. Let's test it. I will reboot the system. The system is rebooting, and I'll pause the video until the system is up and running. Okay, it's ready. I'm opening a terminal and checking if the iptables rules have been loaded into memory. First, I'm becoming root. And then I'm running iptables -v-nl. And the rules are there. They have been loaded by iptables persistent. Now if you want to update the persistent rules with new rules, you simply add new rules and redirect the output of iptables save to the same file. Let's see an example. Suppose we add another rule that's dropping incoming packets from a given network. iptables -i input -s 11.0.0.0/16 -j drop. I've used -i from insert and not -a from append to be sure that packets will be dropped. This will be the first rule on the input chain and will drop the packets. If I run iptables -save, okay, we see that the new rule is there. And now the redirection. iptables -save, the output redirection, etc iptables rules.v4. Now rules.v4 contains also my new iptables rule. And all rules from the file will be loaded at system boot time. Okay, that's how we configure iptables rules to be automatically loaded into the RAM memory at system boot time on Debian or Ubuntu-based distributions. Let's move on and take a look at a specific way for Red Hat or CentOS. To save netfilter rules, type the following command as root: service iptables save. This executes the iptables init script, which is different from the iptables command, and runs the iptables save program that writes the current iptables configuration to /etc/sysconfig/iptables. The existing iptables file, if there is any, will be saved as iptables.save. Next time the system boots, the iptables init script reapplies or restores the rules saved in /etc/sysconfig/iptables by running iptables -restore command. Okay, that's how you save and restore the iptables firewall rules on Red Hat or CentOS. That's all. Now you have the knowledge to save and restore iptables rules at boot time. Thank you. In this section, we'll start a series of lectures about iptables basic matches, which are also the most used ones. As I've already told you, each iptables rule has a matching component and an action component. Iptables rules can be constructed to match traffic by protocol type, destination or source address, destination or source network, destination or source port, input or output interface, header fields, or connection state, among other criteria, and these can be combined to create very complex rules. In this lecture, we'll take a look at how to filter traffic based on source or destination IP or network address. We can match packets by source IP address or by source network address using -s or -- source match option. Address can be either a single IP address like 192.168.0.1, a network IP address with a /mask specification like 10.0.0.0/8, or a domain name like www.linux.com. Please note that specifying any name will be resolved with a DNS query, and this is not always a good idea. Let's take a look at some examples. I want to drop all incoming traffic from Linux 2, which has the IP address of 192.168.0.20, okay, from this Linux machine to Linux 1, to the firewall. And I write iptables -a input. I am using the input chain because it's incoming traffic, -s, this means the source IP address, and the IP address of Linux 2, of the other machine, 192.168.0.20, -j, and the action, drop. Before hitting enter, I'll ping Linux 1 from Linux 2. Ping is working, and I am hitting the enter key. And ping stopped. If I list the firewall, I see that there are 8 matched and dropped packets. If we want to drop by destination IP address, we use -d or -- destination instead of -s when writing the iptables rule. In the next example, I'll write a rule that drops outgoing traffic to an entire network like 8.0.0.0/8 to this network. At this moment, I can communicate with that network. It's working. And iptables -a output, it's outgoing traffic, so I am using the output chain, -d, and the destination network address, 8.0.0.0/8. -j, drop. Now, ping is not working. And if I list the firewall, I'll see a lot of matched packets. There are 2 dropped packets. So this rule drops any packets destined to an IP address that starts with 8 or its first byte is 8. Perfect. Let's continue on and see another example. I want to completely deny access from this Linux machine to a website like, say, www.ubuntu.com. For this task, there are more possibilities. The first one is to find the IP address or the IP addresses, if there are more, of www.ubuntu.com and then drop all the packets that are going to those addresses. You can find the IP address of a website using either nslookup or dig. nslookup www.ubuntu.com. And we see the IP addresses of www.ubuntu.com. And dig www.ubuntu.com. These are the IP addresses of that website. Keep in mind that nslookup works both on Windows and Linux, but dig is a Linux-only command and has more options available. We notice that there are 6 IP addresses for this domain. If we want to deny access to the website, we must write 6 iptables rules, and each rule will drop one IP address. I'll write just an iptables rule as an example. iptables minus a output, this is outgoing traffic, minus d, and I'll take an IP address from this list. Let's say the first one. Minus j drop. Of course, at this moment, the access to the website is not denied because there are still 5 IP addresses that are permitted. The second possibility is to use the domain name in the iptables rule. It will automatically query the system DNS server for the IP addresses and add a rule for each IP address. iptables minus a output minus d www.ubuntu.com minus j drop, and iptables minus v nl. I am listing the firewall. And we notice that there are 6 rules, one rule for each IP address, that drop the outgoing traffic to those IPs. If I open up a browser window and try to connect to www.ubuntu.com, it won't work. The website is not loading. Notice that when dropping traffic based on source or destination IP address and you use a domain name instead of an IP address, at the end, iptables still uses IP addresses and not the domain name. I've used a domain name, but iptables uses IP addresses. This requires access to a DNS server, and that means other iptables rules that allow DNS traffic. Pay attention, especially when using the drop policy. It may be the case when you cannot permit or deny traffic to or from an IP address because you have specified the domain name, but the DNS traffic that resolves the domain name is not permitted. Also note that it's not a good idea to accept or drop traffic to a very big website like google.com or facebook.com this way. Domains like google.com have tens or hundreds of IP addresses, and the DNS response will contain only a few of them. You should use an application firewall like Squid instead of iptables. At the end of this lecture, I just want to tell you that if you see the address 0/0, it means any IP address with any network mask. For example, I accept all outgoing HTTPS traffic and I write iptables minus a output minus ptcp minus d port 443, this is HTTPS traffic, minus d, and now the destination IP address. And I write 0/0. It means any IP address with any mask. Minus j accept. Okay, that's all about matching by source or destination IP address. Thank you. In this lecture, I'm gonna talk about filtering packets using an IP range. When creating your iptables firewall, it's important to keep it as simple as possible. It's always preferable to use a single rule that does the job of other 10 rules. If we want to accept or drop packets from the IP address in the range of 10.0.0.0.10 to 10.0.0.29, we have to write 30 different iptables rules, and this is not scalable at all. The -s and -d iptables matches are used to match traffic from a single IP or network address. It's not possible to specify a range of IP addresses. Fortunately, there is another match that allows matching traffic sourced from or destined to a range of IP addresses. That match is -m IP range. And there are two different options. -src- range used to match by source IP address in the specified range, and -dst- range, which is used to match by destination IP address in the specified range. This is an example that's dropping incoming TCP packets to port 25, which is SMTP, if the source IP address is in range of 10.0.0.10 and 10.0.0.19. The first iptables rule is dropping incoming SMTP packets to port 25 if the source IP address is 10.0.0.10. The second rule is dropping traffic if the source IP address is 10.0.0.11 and so on. I'm sure you can imagine that it's not scalable at all. If you want to drop 100 IP addresses, you have to write 100 iptables rules. Now, instead of writing 10 rules, I could simply write a single rule using -m IP range match option. Let's see how it's done. All these 10 rules can be replaced by a single rule like this. iptables -a input -p TCP -d port 25 and -m IP range -src range. I'm matching by source IP address and the range 10.0.0.10, the first IP address, a minus sign, and the last IP address 10.0.0.19 and -j drop. Now I can comment out these 10 iptables rules and the final result will be the same. I'm commenting out the rules. I'm saving the script and then run it. iptables -vnl. I am listing the firewall. And we see the rule. It's always easier to understand and manage a firewall with fewer rules. Another match that we can use is -m ADDR type, which comes from address type. We can match packets based on the type of the address. There are many address types, but the most important and used ones are unicast, multicast, and broadcast. You can see all the types by executing iptables -m ADDR type -help. These are the types. And I'll show you an example. I'm dropping all outgoing multicast packets or outgoing packets that have the destination IP address of type multicast. I suppose I don't want to advertise or join to any multicast group. iptables -a output -m ADDR type -DST -type multicast -j drop. Hello everybody and welcome back. In this lecture, I'm gonna show you how to filter traffic by TCP or UDP ports. This is a very common task when developing a firewall. You can match by a single port using the match option -d port, which comes from destination port, or -s port, which comes from source port. It's mandatory to specify TCP or UDP protocol using -p match option, otherwise you'll get an error. Keep in mind that there are ports in the packet header only if the protocol is TCP or UDP. Other protocols, like for example ICMP, do not use ports at all. In this example, we are dropping incoming SSH packets. It's incoming traffic because the chain is input, the protocol is TCP, and the destination port is the standard SSH port. We assume that there is an SSH server that is listening on port 22. If we want to match by multiple ports, we can write more iptables rules, one rule for each port, or we can use another option, which is -m multiport. There are two other options, -s ports to match by source ports and -d ports to match by destination ports. After that match option are coming the ports separated by commas. Let's take a look at this example. We are accepting outgoing traffic, it's the output chain, to port 80 or 443. This means traffic destined to HTTP or HTTPS servers. Perfect. Let's go to a terminal and see some live examples. From Linux 2, I want to see what ports are open on Linux 1. In order to check what ports are open, I'll use nmap, which is by the way a great port scanner. nmap and the IP address of the other Linux machine, 192.168.0.10. After a few seconds, nmap will show us what ports are open on Linux 1. As you can see, there are 4 ports open. 22 for SSH, 25 for SMTP, 80 for HTTP, and 443 for HTTPS. I've flashed all the rules, so at this moment it's an open firewall and all traffic is accepted. This is the state where I'm starting from in each example I'll show you. There is no rule and the default policy is set to accept. And I want to drop incoming traffic to port 25. iptables -a input x incoming traffic -p TCP -d port 25 -j drop. And I am listing the firewall again. We can see the rule here and there are no packets matched. I'm scanning Linux 1 again from Linux 2 using nmap. I'm executing the same command again. And we notice that port 25 is now filtered. By the way, do you know what is the difference between a filtered and a closed port? A filtered port is in fact an open port, but there is a firewall that's dropping traffic to that open port and we are receiving no traffic back when sending a packet to that port. In this case, port 25 is open on Linux 1, so there is a process that's listening on that port, but it appears filtered to Linux 2 because packets are dropped. On the other hand, a closed port is a port on which no application is listening. If we send a packet to a closed port, we receive a packet back indicating that the port is closed. That's a TCP packet with the reset flag set. For example, port 55 is closed. So as a conclusion, a filtered port is an open port that doesn't respond back because a firewall is dropping the packets, and a closed port is a port where no application is listening and it responds back with a TCP reset packet indicating that it's closed. Now on Linux 1, if I list the firewall, I'll see some matched packets. There are 2 matched packets. Let's try other examples. I want to block all incoming traffic to port 80. Let's check if port 80 is open, closed or filtered. And it's open. I'm gonna create a new firewall rule that will block all incoming traffic to port 80. In fact, it's the same rule, just that instead of port 25, I have port 80. I'm listing the firewall, there is no matched packet, and if I scan it again, we see that the port is filtered and there are matched packets. There are 3 matched packets. Let's move on and see another example, which is a very common and useful one. We suppose there is a Linux server and a management station, and we want to allow only the management station to connect to the Linux server using SSH. Or, in other words, we allow a single source IP address to connect to Linux 1 using SSH. In this example, it will be the IP address of the Windows recording machine. All other source IP addresses will be denied. Let's check what is the IP address of this Windows machine. I'm running ipconfig and we see that the IP address is 192.168.0.112. Okay. For this task, I'm gonna create a bash script, write the rules inside the script, and then execute the script. It's easier to manage the firewall this way. The first line of my script is the shebang and indicates that this script will be run by the bash shell by default. First, I flush the filter table of all chains because maybe I'll run the script many times and I don't want the rules to be appended each time I run the script. iptables -f. We've already discussed about this in a previous lecture. And the first iptables rule will permit SSH traffic from that specific IP address. iptables -a input -p TCP minus D port 22 minus S and the IP address of my Windows machine. Minus J, accept. This rule is accepting the traffic that is coming from the Windows machine. Now you can imagine that we still need something that will drop SSH traffic that is coming from other source IP addresses. There are two possibilities. If the default policy for the input chain is set to drop, it means that the traffic that is not matched by any rule will be dropped by the policy. In this case, we don't need to write another iptables rule. But if the policy is set to accept, then we mandatory need a second rule that drops all incoming SSH traffic that was not accepted till that point. In this example, I said nothing about the policy, so I'll write that second rule. iptables minus A input minus P TCP minus D port 22 minus J drop. I don't specify the source IP address, and that means any IP address. If you want to specify an IP address, you can simply write minus S 0/0. It's the same. Perfect. That should be enough. Let's save the script and make it executable. Before running the script, I want to check that port 22 is open. So I'm scanning it using nmap from Linux 2. It's open. Now I'm running the script. Let's scan the port again. And the port is filtered. The firewall is dropping the packets that are not coming from the allowed IP address. Linux 2 doesn't have the permitted IP address. If we list the firewall, we see there are dropped packets. From Windows, I am opening PuTTY and trying to connect to Linux 1. I'm writing the IP address of Linux 1. And open. And we see that the port is open. Packets are permitted through the firewall. There are 18 packets accepted by the first rule. In the last example of this lecture, I'll show you how to match by multiple ports in a single iptables rule using -m multiport match option. I'll try to block the access to port 80 and 443. I'll write the iptables rules inside the same script. iptables -a input -ptcp -m multiport -d ports 80, 443 -j drop. Take care that there is an S at the end. So D ports, not D port. And I'm saving the script. Before running it, I'll check the state of those two ports. Port 80 and 443. And they are open. I'm running the script and then scanning the ports again. Okay, the host is not responding at all and nmap thinks that it's not up. I'll add -p, an uppercase P and 0 to avoid probing the server using pings. Now it says that the ports are filtered, exactly what we've expected. There are 8 matched packets by the rule. In the last lecture, we've seen how to match traffic by TCP or UDP ports. But how can we match the traffic of the protocols that don't use ports? The only protocols that use ports are TCP and UDP, and there are a lot of other protocols out there that don't have the concept of port. Some examples are ICMP, GRE, or routing protocols like OSPF or EIGRP. We can see a list of protocols in /etc protocols. These are the protocols I'm talking about. Excepting TCP and UDP, they are not using ports. There is one major thing about protocols which should be cleared up. Network communication happens on many layers, and each layer has its own set of protocols. The scope of iptables is limited to the transport layer and below, so we are talking in fact about layer 3 and layer 4 protocols. Be careful not to confuse protocols and service names. Popular services like SSH, HTTP, SMTP, etc. have been assigned to specific ports. So to match by layer 4 protocol, use the -p option followed by the protocol name. For example, I'll allow only TCP and UDP traffic both on input and output chains. All other traffic like OSPF, GRE or ICMP will be denied by the policy. I am creating a new script called only TCP UDP.sh. As usual, I'm flashing the firewall at the beginning of the script. I'm starting from ground up. Then I'm setting the drop policy on input and output chains. It's always a good idea to allow loopback interface traffic. We'll talk about the traffic of the loopback interface in the next lecture. -I and the name of the loopback interface, -J accept. -O, the outgoing interface, the same LO, -J accept. These two rules accept the loopback interface traffic. And the rules that are accepting TCP and UDP traffic on input and output chains. iptables -A input -PTCP -J accept. iptables -A output -PTCP -J accept. And the same for UDP. This firewall script is accepting only TCP and UDP traffic. All other kind of traffic will be dropped by the policy. I am saving the script, make it executable, and then run it. TCP and UDP are working, for example, dig www.google.com. I am testing the DNS protocol, that means UDP, it's working, but ping, which means ICMP, will not work. Operation not permitted. Packets are dropped by the policy. There are 6 dropped packets, and we can also see 6 messages. Welcome back. In this lecture, we'll take a look at how to match packets based on the interface they are coming to or the interface the packets are going through, are leaving our station. If we want to match packets based on the interface via which they were received, we use the -i option and then the name of the incoming interface. In this example, I allow any incoming packets that are received on the wireless interface named WLAN 0. This option -i is available only for packets entering the input, forward and pre-routing chains. To match traffic by outgoing interface, use -o option and then the name of the outgoing interface. In this example, I allow any outgoing packets leaving our station through the interface named ENP8S0. Also note that this option is available only for packets entering the forward, output and post-routing chains. Also note that if the interface name ends in a plus sign like this, then any interface which begins with this name will match. Also keep in mind that it's always good practice to permit traffic on the loopback interface, which is called LO. By the way, the loopback interface is a special virtual network interface that your computer uses to communicate with itself. It is used mainly for diagnostics and troubleshooting and to connect to servers running on the local machine. Let's take a look at an example. I want to allow incoming and outgoing traffic through the loopback interface. iptables -a input, -i LO, -j accept. And iptables -a output, -o LO, -j accept. You can always add these two rules at the beginning of your firewall script. We'll see later that we can create more complex rules using these matches. For example, we can load balance traffic based on the outgoing interface. Imagine we have a Linux router with two internet connections and say SSH, HTTP and HTTPS traffic leaves the router on the first interface, which is in fact the first internet connection, and email traffic leaves the router via the second interface or the second internet connection. We'll dive deeper into this in the NAT section. At this point, we've seen many examples on how to match packets based on certain conditions. However, in some cases, you may need to negate these matches. iptables provides the negation operator, which is an exclamation mark, for this purpose. A very common use case scenario is to allow traffic to a specific service only from a given IP address. Let's say we have a web application that uses the HTTPS port that can be used only from a specific IP address or network. And the iptables rule that does this is iptables -a input, not -s, and the IP address of the allowed host. For example, the IP address of Windows. -p TCP -d port 443 -j drop. This will drop all TCP traffic that's coming to port 443 except that from 192.168.0.112. Or, in other words, if the source IP address is not this IP, drop the packet. Let's test it. I'll check the HTTPS port from Windows. and I'm using telnet to scan the port. Telnet, the IP address of Linux 1, and the port. And we'll see that the port is open. Now, let's scan the port from Linux 2. I'll use the same telnet command. Telnet and the IP address of Linux 1. And the port. Sorry, the command is telnet. And it's not connecting. The port is filtered. Only the IP address of the Windows machine is allowed to communicate with this port. Negations are very useful sometimes. Nowadays, most of the network traffic uses TCP. Web, email, FTP, telnet, SSH, and so on. All these protocols use TCP as the layer 4 protocol. It's common to match traffic based on TCP flags. For example, each new connection is established by packets with SYN flag set. To match packets that have the SYN flag set, there is the --SYN option. It matches when only SYN flag is set. Another possibility is to use --TCP- flags match option, which has two arguments. The first argument is called mask and represents the flags which we should examine, written as a comma-separated list. The second argument, called comp, is a comma-separated list of flags which must be set. To match by TCP flags, you should know which are these flags. SYN comes from synchronize and is used for TCP three-way handshake or connection initialization. The first packet of any TCP connection has this flag set. ACK comes from acknowledgement, and every TCP packet has it set excepting the first one, which has only the SYN flag set. FIN or FIN comes from finalize and is used for closing the connection. RST comes from reset and is another possibility to close the connection. Then there are URG from urgent and PSH from push. These last two flags are not used too often. And all, which means all TCP flags are set, and none, which means that no TCP flag is set. Let's see some examples. I want to block incoming TCP connections to port 22. To do that, I could block only the first TCP packet, the packet that initializes the connection, and that packet has the SYN flag set. I'm scanning port 22 on Linux 1 from Linux 2 to see if it's open. Nmap -p22 and the IP address of Linux 1. And it's open. Back on Linux 1, I'll add an iptables rule that drops incoming TCP packets to port 22 if they have the SYN flag set. iptables -a input -ptcp -d port 22 -SYN -j drop. Back on the other Linux machine, I'm scanning port 22 again. And it's filtered. The firewall is dropping TCP packets with SYN flag set. If we list the firewall, we see that there are dropped packets. There are two dropped packets. Let's try another example. I want to permit incoming SSH connections only from a specific IP address. Maybe there's a management station or a location from which SSH is allowed. In this example, the permitted IP address will be the address of Windows. How can I do that? First, I'll clear the firewall. I want to start from ground up. Now there is no rule and the policy is set to accept. For this task, I'll use an iptables rule similar to the last one. Actually, I'll add another match with a negation. This is the last rule. And I'll add this option, NAT -s and the allowed IP address, the IP address of Windows. This part means match the packet if the source IP address is not this one. We can describe the entire rule like this. If incoming packets are of type TCP with the SYN flag set and the destination port is 22, drop them if the source IP address is not 192.168.0.112. Or in other words, only this IP address is allowed to establish a new SSH connection. I'll scan port 22 from this Linux machine. And it's filtered. And the same from Windows. This is the allowed IP address. I'm using telnet. Telnet and the IP address of Linux 1. And port 22. And the port is open. Of course, you can also test it using PuTTY. We notice that the port is open. Hello and welcome back. In this lecture, we'll dive into stateful firewalls. NetFilter has a module called Contract that permits us to inspect and restrict network connections using a method called connection tracking. Connection tracking refers to the ability of maintaining state information about a connection in memory tables. Firewalls that do this are known as stateful and are much more secure than their stateless or packet-based counterpart. The decision to drop or to accept a packet is not taken anymore based on the values in the packet headers like source or destination IP addresses or ports, but on the relation the packet has with other packets. For a packet, there are the following states defined. A new packet is the first packet of any connection. It's in fact the packet requesting a new connection, such as a TCP packet with the SYN flag set or the first ICMP echo request packet. Packets in the established state are those that are already part of an existing connection. All packets of the connection starting with the second packet and until the last one are in the established state. Related packets are those that are requesting a new connection but are already part of an existing connection, such as FTP data transfer or an ICMP error. In general, it's good practice to accept these packets. An invalid packet is not part of any connection in the connection tracking table. These packets cannot be identified in any state. Generally, it is a good idea to drop everything in this state. And the last state is called untracked and it's not so often used. Briefly, if a packet is marked within the raw table with the no track target, then that packet will show up as untracked in the state machine. Note that you can use the stateful functionality of iptables connection tracking with any network protocol even though the protocol itself is stateless, such as UDP or ICMP. To match packets based on their state, use -m state, --, state, and then a comma separated values of packets states written in uppercase letters. In this example, we are accepting incoming packets if they are already part of an existing connection. Another rule or the policy of the input chain could drop the first packet of the connection which is in the new state. This means that the host can connect to any destination using any protocol, but no one is allowed to connect to services running on the host. This was just an introduction to stateful firewalls. In the next lecture, we'll see a real example of how to configure a stateful firewall using iptables. In the last lecture, we've discussed about stateful firewalls and how do they work. Let's go to the terminal and create a stateful firewall from scratch, which is very good for a desktop operating system. This is the kind of firewall I'm using on my personal laptop, and I can say that I haven't had any problems in years. I'm gonna create a bash script that contains all iptables rules. At the beginning of the script, I'm flashing the filter table of all chains, iptables -f. Then I allow loopback traffic. Always allow loopback traffic on input and output chains. iptables -a input, -i, the incoming interface, LO, -j accept. And the same for the output chain. Now we have the outgoing interface, which is LO, -j accept. The loopback traffic is permitted. The rules until this point could be part of any firewall. I'm starting the stateful firewall part. As I said earlier, it's a good idea to drop invalid packets on input and output chains. These are the packets that cannot be identified in any state. iptables -a input, -m state, --- state, invalid. -j drop. And the same for the output chain. This kind of firewall is very good for a desktop operating system. This means that there are no services running or no one connects to them from the outside. The host communicates to any destination and uses any protocol, so all outgoing traffic is permitted, but only the return traffic is allowed. This means that I should accept on the input chain only the packets that are in the established or related states. This is the return traffic. And on the output chain, I'll allow packets that are in new, established, and related states. It means all traffic, including packets that initialize new connections. iptables -a input, -m state, --- state, established, comma related, -j accept. Always write the states in uppercase letters. And the rule for the output chain for outgoing traffic. iptables -a output, -m state, --- state, and we have new packets that establish new connections, established, and related. -j accept. And finally, I set the policy to drop on input and output chains. All traffic that was not priorly permitted will be dropped. iptables -p input drop and iptables -p output drop. That's all. I'm saving the script and then make it executable and run it. Let's test outgoing traffic. Ping 8.8.8.8. And ping is working. Let's test HTTP or HTTPS. HTTPS is working. And I also test SSH. I'm going to connect to Linux 2. And SSH is working. Perfect. Now, let's test new incoming connections. From Linux 2, I'll ping Linux 1. Ping and the IP address of Linux 1. And ping is not working. Packets are dropped on the input chain. Let's test SSH. SSH is not working. All packets that initialize new connections are dropped on the input chain. No new incoming connections are allowed, and this is secure. Let's list the firewall. And we see packets dropped by the policy on the input chain. There's also an invalid packet that has been dropped. This is very good, but however, there are cases when we want to allow new incoming connections from a specific IP address or protocol. For example, we want to allow incoming SSH connections only from a management station, so from a given IP address. How could we do that? It's very simple. At the beginning of the script, we add a rule that permits incoming TCP packets which are in the new state if the protocol is SSH and the source IP address the given one. In the same script, somewhere at the beginning, I'll add a new rule. In fact, it doesn't matter where I add the rule, but it's better to be at the beginning because I want to permit the packet fast now after many other rules have been checked. So iptables -a input minus ptcp minus dport 22, and now the new state -m state minus state new minus s the given IP address, the IP address that is allowed, and it's Linux 2. -j accept. I'm saving the script and then test it again. I'm running the script, and from Linux 2, I'll try to connect using SSH to Linux 1. And now SSH is working. Perfect. Let's list the firewall again. And we see there's one packet that has been accepted by the new rule. Welcome back. If you want to match packets based on source MAC address, use the -m MAC match option. Note that you can filter Ethernet or wireless traffic only by source MAC address and not by destination MAC address. This match could be very useful sometimes. Imagine you have a server in your local network and want to allow only a list of trusted machines to access the services that are running on the server. Or you have a NAT router that is running Linux and want only the corporate devices to access the internet. Or in other words, you don't allow devices that are not yours or trusted in your network. Keep in mind that MAC addresses are only valid inside the local area network. The first router towards destination will change the source MAC address of the packet with its own MAC address, the MAC address of its outgoing interface. Also note that you cannot impose a strong security policy based on MAC addresses because MAC addresses can be spoofed easily. When we want to match packets by source MAC address, we use -m MAC match. In this example, we are dropping any incoming packets, it's the input chain, that are coming on WLAN 0 interface and have that given source MAC address. Let's see two more use cases. The first task is to drop incoming packets that are coming with a specified MAC address, and the second task is to configure the net router, which of course is running Linux, to permit the access to the internet only to a list of trusted devices or MAC addresses. Let's do the first task. I'll drop all incoming traffic to Linux 1 if the source MAC address is that of Linux 2. MAC belongs to layer 2, so if you are dropping by MAC address, you are dropping all protocols like IP, ICMP, TCP, UDP, and so on. First, I want to test that the connection between Linux 2 and Linux 1 is up. Perfect, ping is working. Let's see what is the MAC address of Linux 2. This is the MAC address and I'll copy it to the clipboard. And on Linux 2, I'll write the iptables rule. iptables minus a input, it's incoming traffic, minus m MAC, minus MAC minus source, and I'll paste the MAC address. Minus j drop. Let's ping this host again. We notice that ping is not working anymore. I am stopping the ping command. Back on Linux 1, let's list the firewall. And we see a lot of matched and dropped packets. All packets that have this source MAC address will be dropped. Let's move on and do the second task. I'm gonna create a script and write there all the necessary iptables rules. As in all other examples, at the beginning of the script, I am flashing the forward chain. Because there could be tens of MAC addresses that I must permit, I'll define a new variable and store those MAC addresses in that variable. So this is the name of my new variable, permitted max equals, and a list of MAC addresses separated by comma. The first MAC address, the second MAC address, the third, and so on. I'll change something at each MAC address to have different addresses. It's good practice to write variables in uppercase letters. Don't use spaces on the left and right side of the equal sign and use white space between addresses. Now, using a for loop, I'll iterate over the list of MAC addresses and run an iptables rule for each MAC in the list. So for MAC, this is a temporary variable in $permitted max. Do and done. Between do and done, we have the for block of code. So iptables minus a forward, remember that we are a router, minus m MAC, minus MAC minus source, $MAC, minus j accept. And I'll print out a message to know what the script is doing. Echo $MAC permitted. And finally, I'll set the policy to drop on the forward chain. So all other packets that were not accepted will be dropped. iptables minus p forward drop. Perfect. I am saving the firewall. Then I'll make it executable and run it. We see how these 4 MAC addresses have been permitted. Only the packets from devices with those MAC addresses can access the internet. This kind of script is useful also for a local server. If you want a LAN server to be accessed only by a list of trusted hosts, you just replace the forward chain by the input chain. When you want to add or to remove a MAC address from the list, you simply remove that address from the list, save the script, and run it again. I have removed 2 addresses. Sorry, I've noticed a small error. Here's the forward chain, not input. Okay, I am saving the script and then run it again. Now, only these 2 MAC addresses are permitted. You see that it's very easy to add or to remove MAC addresses from the list. As a sysadmin, you may be asked to control access to a couple of services based upon day and time. For example, the company intranet server should only be available from Monday to Friday between 8 a.m. and 6 p.m. In this lecture, I'll show you how to filter traffic based on the date and time the packet is received, generated, or routed. There is the -m time match that is very flexible and has many options like date start, date stop, time start, time stop, month days, and week days. You can see all options by running iptables -mtime --help. These are all options of -mtime match. Note that by default, NetFilter uses UTC and not the system time. On my computer, it's East European time, which means UTC +2. So the UTC hour is 14, not 16. The ---- kernel TZ option makes NetFilter use the system time instead of UTC time. But pay attention, I've seen different Linux distributions that used only UTC even though kernel TZ option was given. Let's move to a terminal and take a look at some examples. In the first example, I want to permit SSH traffic only between 10 a.m. and 4 p.m. on weekdays, and in the second example, I want to allow access to a specific website only after working hours. We suppose this machine is the router. I'll create a script and write all iptables rules in that script. First, we flush all chains because we'll execute the script many times and don't want the rules to be added each time we execute the script. We want to permit incoming SSH traffic only between 10 a.m. and 4 p.m. or 16 on weekdays. So iptables -a input -p TCP -d port 22. This is SSH traffic -m time -time start 10:00 and -time stop 16:00 -j accept. Use 24 hours format when writing the time. And another rule that drops packets if time is not between that time interval. This is necessary only if the policy is set to accept. In fact, it's the same rule, but without the -m time match. This is the second rule. And of course the target is drop. The rule on line number 6 will drop packets that haven't been accepted by the rule on line 5. I'm saving the script, then make it executable and run it. From the other Linux host, I'll connect to the firewall using SSH. And SSH is working. Packets are permitted. I'm listing the firewall. And we notice that 13 packets have been accepted by this rule. We are in that time interval. Look how it used UTC and not East European time. So in fact it's 14, not 16. To test it properly, I'll change the time when the rule that accepts the traffic is active. Let's say that the traffic will be permitted only between 3 and 5 a.m. 3 and time stop is 5. This is AM time. I'm saving it and then run it again. From Linux 2, I'll try to connect using SSH to Linux 1. And it's not working. The rule that accepts SSH traffic is not active at this time. It's active only between 3 and 5 UTC. We notice 5 dropped packets by the second rule. Let's move on to the second task. We want to allow access to a specific website, let's say www.ubuntu.com, only after working hours. This machine is the router and this is routed traffic, and that means the forward chain. In the same script, I'll add a rule to forward chain that matches HTTPS traffic to www.ubuntu.com. iptables -a forward -p TCP -d port 443. This is HTTPS -d www.ubuntu.com. And now matches related to time, -m time, -time start 18, this means 6 p.m. UTC, -time stop 8:00, -j accept. And the rule that drops outgoing HTTPS traffic to www.ubuntu.com. This is the traffic that hasn't been accepted by the first rule. This is the second rule, and it has the drop target. If the destination IP address is that of the domain www.ubuntu.com and time is between 18 and 8, the packet will be accepted. Otherwise, it will be dropped by the rule on line 10. I'm saving the script and running it. We notice the rules that accept packets destined to the IP addresses of www.ubuntu.com between 18 and 8 UTC, and the rules that are dropping the traffic to the same domain name or the same IP addresses if the time is not in that interval. Sometimes I'm asked by my students, how do I restrict the number of connections with the same source IP address to my server on port 80 or 25? NetFilter has the conlimit module, which allows you to restrict the number of parallel connections to a server per client IP address, or client address block. We can, for example, permit just 10 new connections to our email server from the same IP address, or 5 parallel HTTPS connections from another IP address. This net filter option is very useful to protect against denial of service attacks. This example uses con limit match to reject incoming TCP connections to port 25, which is SMTP, if the number of connections from the same IP address is above 5. Notice that in this example, I've used another target, which is reject. Instead of silently dropping the packet, the reject target is dropping the packet and then responding back to the source with a TCP reset packet. We'll have a dedicated lecture on reject target, and we'll see what are the differences between drop and reject and when to use each of them. In this lecture, we'll take a look at the limit match, which is, by the way, one of my favorites. The limit match uses a token bucket and restricts the rate of matches. It will only match a given number of times per unit of time. The -m limit match has two options. The first is -- limit, followed by a number which specifies the maximum average number of matches to allow per second. It's possible to specify units explicitly using /second or /minute or /hour, like, for example, -- limit 10 /minute, which means 10 matches per minute. The second option is -- limit burst, followed by a number indicating the maximum burst before the above limit kicks in. By default, limit burst is 5. For every time unit specified using -- limit option that passes without a match, one of the bursts will be regained. This limit match can be used in combination with the log target to do rate-limited logging. Let's take a look at two examples. In the first example, the default limit burst is 5, and that means that the first 5 packets will be logged no matter how fast they arrive. After that, we log only 1 packet per minute because the limit is 1 per minute. This match is useful to avoid various denial of service attacks. Let's take a look at the second example. The iptables rule is accepting 7 new TCP connections because the limit burst is set to 7, no matter how fast they arrive. And after that, it will accept only 2 new connections per second because the limit is 2 per second. If in a second there are not 2 new connections, the burst which has been probably spent will be filled. For every second that passes without matching 2 packets, the burst will be regained with the number of packets not matched in that second. Like if in a second only 1 packet is matched, then 1 burst will be regained, and if in another second no packet is matched, then 2 bursts will be regained. Now I'm going to a terminal and show you a live example. On this Linux machine, I want to limit incoming ping packets to 1 per second with a burst of 7. First, let's see the help of -m limit match. iptables -m limit --help. And we see those 2 options we've just talked about, -- limit and -- limit burst. For this example, we need 2 iptables rules. The first rule will match and accept incoming ping packets, which are in fact ICMP echo request packets, at a rate of 1 per second and a limit burst of 7. iptables -a input -p ICMP minus minus ICMP minus type, echo request. These are ping packets, minus m limit, minus minus limit 1 slash sec, minus minus limit minus burst 7 minus j accept. Let me explain to you this rule in detail. The rule accepts incoming ICMP echo request packets, and there is like a deposit or burst of 7 packets that will be accepted no matter how fast they arrive. After those 7 packets, only 1 packet per second will be accepted. If there is a second when no packet will arrive, the deposit or the burst will be filled. And we need a second rule to drop packets that haven't been accepted by the first rule. It's in fact the same iptables rule without minus m limit match and with the drop target. Instead of accept, we have drop, and there is no minus m limit match. And of course minus j. Perfect. Let's list the firewall. And we see those 2 rules we've just written. To test it properly, I want to see all incoming ping packets dropped or accepted. And I'm starting TCP dump, which is a sniffer and packet analyzer like Wireshark, just that it's working in console. It doesn't have a graphical interface. TCP dump, ICMP, I want to see only ICMP traffic, minus n. Minus n comes from numeric, and it's used not to convert addresses and ports to names. It will show them in numeric format. From Linux 2, I'll send to Linux 1 10 echo request packets per second. Ping minus I 0.1 and the IP address of Linux 1. Minus I specifies the sending interval in seconds. It means 10 packets per second. Okay, it's too much. It says I cannot flood. Okay, I'm becoming root and I'm executing the command again. Now it should work. And it's working. Perfect. I'm interrupting the command by pressing Ctrl+C. We noticed how we received 7 replies very fast and then only 1 reply per second. If you look here at this number, you see that the first 7 packets have been accepted and the next 3 have been dropped by the firewall. It skips from 7 to 11. Let's go to server 1 and see the output of TCP dump. Let's go at the beginning. Here. Okay. We notice how these 7 packets have been accepted. 1 echo request, the second echo request, the third, the fourth, and so on till the 7th. These are the first 7 echo request packets. And then only 1 packet per second has been accepted by Linux 1, and for each accepted packet, an echo reply was sent back to Linux 2. Linux 1 has sent 10 packets per second, 9 have been dropped, and 1 accepted. We see how these 3 packets have been dropped. So there is no echo reply for an echo request. This echo request has been accepted and an echo reply sent back to the source. Then Linux 1 has sent 10 packets per second. These are 10 packets, 9 have been dropped and 1 accepted. I'm interrupting TCP dump by pressing Ctrl plus C. I'm listing the firewall iptables minus VNL. And we notice both accepted and dropped packets by the iptables rules. That's all about the limit match. Thank you. Hello guys and welcome back. I'm very excited about this part and I can say that this is one of my favorite iptables features. The discussion in this lecture will be about the recent match. The recent match allows us to build a temporary list of denied IP addresses based on whatever criteria we want and then drop any incoming packets from those IP addresses for a given amount of time. We could, for example, build a dynamic database of IP addresses that have scanned our server and then drop all traffic coming from those IP addresses. Let's take a look at this example and I'll start with the second iptables rule, which is dropping routed traffic entering interface called Ethernet 0 if the protocol is TCP and the destination port is 8080. Simultaneously, a list named bad guys is created and the source IP address of that dropped packet will be added to that list. Later, when a packet arrives and must be routed, it will be inspected by the first rule. The first rule is checking if the source IP address belongs to the bad guy list. This is the name option, and if it's in the list, it will be dropped. The update option updates the last seen time of that particular source IP address, creating a so-called quiet time. Therefore, there must be a quiet time of 60 seconds before another packet from this address will ever be considered. Or in other words, if 60 seconds pass without seeing again that IP address, the subsequent packets from the source IP address will be again permitted. Of course, if they won't be dropped by the second rule, in which case the source IP address is added to the bad guy list again. Okay, let's move on and take a closer look at these match options. The -- name option is creating a list in which the source IP address will be added and checked. -- set is adding the source IP address to the list. And --rcheck is checking if the source IP address is already in the list and doesn't update the last seen time. If the source IP address is in the list, any packet from that source IP address will be dropped for that absolute number of seconds specified. The update option is checking if the source IP address belongs to the list and updates the last seen time. After the last seen time passes without another packet to update it, the source IP address will be allowed to communicate again. This creates a temporary ban or a quiet time. The seconds option is used with update or rcheck and matches the packet only if the source IP address is in the list and the last seen time is valid. Note that the list with blacklisted IP addresses is found in /proc/net/xt_recent/ and the name of the list. Let's go to a terminal and see some live examples. Let's assume that no one is allowed to access port 25 TCP from the outside. And to make it more interesting, I'll say that it's not allowed to access the port between 8 and 10 p.m. UTC time. If someone tries to connect or scan port 25, which is SMTP between 8 and 10 p.m., the source IP address will be added to a list named hackers, and all subsequent packets from that IP address will be dropped for 60 seconds. I'll create a script called recent.sh. I'm creating an iptables rule that's dropping incoming TCP traffic to port 25 between 8 and 22 or 10 p.m. And besides the rule, it will create a list called hackers and add the source IP address of the packet to the list. iptables -a input x incoming traffic, the protocol is TCP, the destination port 25 SMTP, -m time, -time start, and I said 8 a.m. and -time stop 22 or 10 p.m. Use the 24-hour format. And the recent match, -m recent. If I want to continue the rule on the next line, I write a backslash and I press the enter key. And I continue writing the rule. -name hackers, -set, -j drop. Let me explain to you the rule again. When the first TCP packet to port 25 arrives, if the time is between 8 and 10 p.m., the packet is dropped. A list called hacker is created and the source IP address of the dropped packet is added to the list. --name creates the list and --add adds the source IP address to the list. The second step is to add another rule that drops all incoming packets if the source IP address is already in the hackers list. In addition, the last seen time is updated with another 60 seconds. The source IP address will stay in the list for another 60 seconds. This is done by using the update and seconds options. This can be the first rule to drop the packets earlier. So iptables -a input, -m recent, -name hackers, the list, -update, and -seconds 60, -j drop. If no more packets are coming from that source IP address for at least 60 seconds, new packets from that blacklisted source IP address will be allowed again. Of course, if there is no other rule that's dropping the packets. Let's test it. I'm setting the execution permission on the script and running it. First, I'm checking the time. And we are between 8 and 22 or 10 p.m. Pay attention that iptables uses UTC time, not local time. From Linux 2, I'll continuously ping Linux 1. Ping is working, and I'm opening a new terminal and scanning port 22 on Linux 1 using nmap. nmap -p25 and the IP address of Linux 1. And ping has stopped. That's because the IP address of Linux 2 has been added to the hackers list and all packets will be denied for 60 seconds if no other packet arrives at Linux 1. The port is filtered. I'm stopping the ping command by pressing Ctrl+C because I want you to notice the quiet time. On Linux 1, I am listing the firewall, iptables -vnl, an uppercase L. And we see the rules and how many packets were dropped. there's only one packet matched and dropped by this rule, the second rule. That's the first scanning packet. And many other packets dropped by the first rule because the IP address of that packet belongs to the hackers list. When listing the firewall, you notice that we don't see the contents of hackers list. To see its contents, we should display a file from /proc directory. cat/proc net xt_recent and the name of the list, hackers. And we see here the source IP address of Linux 2, which was added to the list and denied, and the updated last seen time in form of a Unix timestamp. There are more last seen times because more packets arrived and each packet has updated this timestamp. Now remember that we have a quiet time of 60 seconds. I think that the time has already passed. Let's check again if ping is working. And ping is working again. 60 seconds have passed without a packet with the source IP address of Linux 2 to be received by Linux 1. But if I send a new SMTP packet to Linux 1, the source IP address will be again banned for another 60 seconds. And I'm scanning port 25 again. The port is filtered and we notice how ping stopped. The IP address of Linux 2 has been added to the list again. In this video, we'll take a look at another interesting match called quota. But what is quota? Generally speaking, quota is a limit set by a network administrator that restricts some aspects of the file system, such as the amount of disk space that can be used by a single user, or the amount of traffic sent or received. In the context of netfilter and IP tables, quota is used to limit the number of packets or bytes matched by an IP tables rule. When the quota is reached, the rule doesn't match anymore. In this example, I'll accept only 1 GB of outgoing HTTP traffic from this Linux machine, which is the web server, to that specific IP address. This means that 80.0.0.1, which is the destination in this case, and our Linux machine, the source, cannot download more than 1 GB of data using HTTP. If more than 1 GB of outgoing traffic is transmitted, the first rule which accepts the packets becomes inactive, and the second rule will drop the subsequent packets. We can create more complex rules, like for example we can set quota per IP or per MAC address, or in combination with the time match, we can set a quota between a starting and an ending time. The requirement could sound like this. Permit no more than 100 megabytes of outgoing HTTP traffic during working hours from a single IP address. As a reminder, 1 kilobyte equals 1025 bytes, 1 megabyte equals 1025 kilobytes, and 1 gigabyte equals 1025 megabytes. This means that a gigabyte is more than 1 billion bytes, but for the simplicity of this example, we consider 1 gigabyte equals 1 billion bytes. Let me show you a live example. I want to permit only 10 megabytes of incoming SSH traffic from Linux 2 to Linux 1. iptables -a input -s the source IP address of Linux 2 -p TCP -d port 22, that's incoming SSH traffic, -m quota, quota, and a value that represents 10 megabytes of traffic. This value will be given in bytes, so 10 million bytes. -j accept. This rule will be active until the quota is reached, and it means that only 10 megabytes of incoming SSH traffic from Linux 2 will be permitted. And we need one more iptables rule that drops SSH traffic from Linux 2 to Linux 1 when the quota will be exceeded. iptables -a input -s the IP address of Linux 2 -p TCP -d port 22 -j drop. The second rule will drop any packet that hasn't been accepted by the first one, and that means the traffic over 10 megabytes. If I list the firewall, I'll see no matches. Now, on Linux 2, I'll try to connect using SSH to Linux 1. And SSH is working. I've interrupted the connection by pressing on Ctrl+C. I am listing the firewall again, and we notice 12 matches, 12 packets or 2209 bytes. The quota has not been reached. To test it properly, I'll generate more than 10 megabytes of SSH traffic. There are a lot of packets, so it's difficult to simulate this by simply executing commands in the SSH connection. What I'll do is to use SCP, which comes from Secure Copy, and in fact uses SSH to copy files. And I am creating a file that is bigger than 10 megabytes, and after that I will transfer that file using SCP to Linux 1. file.tar/var. Okay, I'm interrupting the command. I don't want an extremely big file, it's enough. Let's check its size. ls -l, an uppercase S, H, and file.tar. It's big enough, it's 264 megabytes. I'll copy this file to Linux 1. This is incoming SSH traffic to Linux 1. The user that authenticates to Linux 1 using SSH, student, and the IP address of Linux 1. Colon, and the destination. Where will the file be copied on Linux 1? In the home directory of the student user. As you can see, the connection stalled. The quota was reached and the new SSH traffic over the quota will be denied. You don't see exactly 10 megabytes because when SCP is displaying the transferred data, it only approximates it. Back on Linux 1, I am listing the firewall. And we notice almost 10 megabytes of accepted data. Remember that 1 kilobyte is not 1000 bytes, but 1024 bytes. So we'll see a value which is a little bit smaller here. Let's see the size of the file. Home, student, file.tar. And it's 9,5 megabytes. Perfect, it's working as I have expected. Thank you.